Welcome to the video lecture series of Basic Electrical Engineering, Module 3, Chapter 1. Module 3, Chapter 1 deals with an important electrical device, because of which till today we are using the AC transmission system. It is one of the main reasons why we are using till today the AC transmission system, even though we use much DC powers. So which is none other than the transformer. So in this module, we'll be discussing about the transformer. If we look at the contents, at first we'll be looking at the construction of the transformer, and then we'll look at the principle of operation, and then we are going to derive a EMF equation for the transformer. Then we'll look at the losses which are going to occur in the transformer, the efficiency of a transformer, and then we are going to look at the types of the transformer. And then we have numericals based on the EMF equation and efficiency. Before going into the actual contents of this transformer, so we need to understand some basic concepts. So first we will look at, or we will go through those basic concepts, and then we will start with the actual contents. So, basics of electromagnetism. So as per the basics law of physics, whenever an electric current flows through a conductor, a magnetic field is formed around the conductor. Whenever an electric current flows through a conductor, a magnetic field is formed around the conductor. So usually we call this as the right hand thumb rule. So as per this law, whenever current flows through a conductor, so surrounding this conductor, a magnetic field will be created. And the direction of the current and the direction of the magnetic field can be identified easily by the right hand thumb grip rule. So as shown in the figure, the thumb indicates, when we hold a conductor, the thumb indicates the direction of the current flowing, and the remaining finger indicates the direction of the magnetic field revolving around the conductor. So in this case, the current is flowing upward and the magnetic fields will be revolving in counterclockwise direction. If the current flows downwards, then the magnetic fields will revolve in clockwise direction. So this can be easily identified or remembered by this right hand grip rule, or we can easily remember that in another way with the help of the screw. So ಒಂದು ಸ್ಕ್ರೂ ತಗೊಂಡು ನಾವು ಆ ಸ್ಕ್ರೂನ ಟೈಟ್ ಮಾಡಿದಾಗ ಅಥವಾ ಆ ಸ್ಕ್ರೂನ ಲೂಸ್ ಮಾಡಿದಾಗ, ಸೊ ಆ ಸ್ಕ್ರೂ ಯಾವ ಕಡೆ ಹೋಗುತ್ತೋ, ನಾವು ಟೈಟ್ ಮಾಡಿದಾಗ ಏನಾಗುತ್ತೆ, ಒಳಗಡೆ ಹೋಗ್ತಾ ಇದೆ. ಸೊ ಆ ಡೈರೆಕ್ಷನ್ ಏನಿದೆ, ಕ್ಲಾಕ್ ವೈಸ್ ಡೈರೆಕ್ಷನ್ ರೊಟೇಷನ್ ಮಾಡ್ತೀವಿ ನಾವು. ಸೊ ಅದೇ ರೀತಿ ನಾನು ಈ ಡಯಾಗ್ರಾಮ್ ಮೇಲೆ ಹೇಳ್ದಂಗೆ ಕರೆಂಟ್ ಅಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ಇದ್ದಾಗ, ಅಂದ್ರೆ ಡೌನ್ವರ್ಡ್ ಹೋಗ್ತಿದ್ದಾಗ, ನಾವು ಸ್ಕ್ರೂ ಟೈಟ್ ಮಾಡ್ಬೇಕಾದ್ರೆ ಏನಾಗುತ್ತೆ, ಡೌನ್ವರ್ಡ್ ಹೋಗುತ್ತೆ. ಆವಾಗ ನಾವು ಯಾವ ಕಡೆ ರೊಟೇಟ್ ಮಾಡ್ತೀವಿ, ಕ್ಲಾಕ್ ವೈಸ್ ಆಗಿ ರೊಟೇಟ್ ಆಗುತ್ತೆ ಕರೆಂಟ್. ನಾವು ಅದೇ ಸ್ಕ್ರೂನ ಅನ್ಸ್ಕ್ರೂ ಮಾಡಿದಾಗ, ಸೊ ಅನ್ಸ್ಕ್ರೂ ಮಾಡ್ಬೇಕಾದ್ರೆ ಏನಾಗುತ್ತೆ, ಮೇಲ್ಗಡೆಗೆ ಬರುತ್ತೆ ಸ್ಕ್ರೂ, ವಿಚ್ ಇಂಡಿಕೇಟ್ಸ್ ದ ಡೈರೆಕ್ಷನ್ ಆಫ್ ಕರೆಂಟ್. ಅಂಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಯಾವ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ರೊಟೇಟ್ ಆಗ್ತದೆ ಅಂತ ಗೊತ್ತಾಗಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ, ನಾವು ಯಾವ ಕಡೆ ತಿರುಗಿಸ್ತಾ ಇದೀವಿ ಸ್ಕ್ರೂನ, ನಾವು ಕೌಂಟರ್ ಕ್ಲಾಕ್ ವೈಸ್ ಅಲ್ಲಿ ತಿರುಗಿಸ್ತಾ ಇರ್ತೀವಿ. ಇದು ಈಸಿಯಾಗಿ ನೀವು ಜ್ಞಾಪಕ ಇಟ್ಕೋಬೇಕು. ಇದ್ರ ಜೊತೆಗೆ ಇನ್ನೊಂದು ಏನು ಕನ್ವೆನ್ಷನ್ ನಾವು ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂತ ಹೇಳಿದ್ರೆ ಡಾಟ್ ಮತ್ತೆ ಕ್ರಾಸ್ ನೋಟೇಷನ್ಸ್ ನ ಯೂಸ್ ಮಾಡ್ತೀವಿ ಕರೆಂಟ್ ಡೈರೆಕ್ಷನ್ ನ ಇಂಡಿಕೇಟ್ ಮಾಡಿ. ಸೊ ಯೂಶಲಿ ಕರೆಂಟ್ ಏನಾದ್ರೂ ನಿಮ್ಗೆ ಏನು ಸ್ಕ್ರೀನ್ ಕಾಣ್ತಾ ಇದೆಯೋ ಆ ಸ್ಕ್ರೀನ್ ಒಳಗಡೆಗೆ ಎಂಟರ್ ಆಗ್ತಾ ಇದ್ರೆ, ಓಕೆ, ಸ್ಕ್ರೀನ್ ಒಳಗಡೆಯಿಂದ ನಿಮ್ ಕಡೆಗೆ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗ್ತಾ ಇದೆ ಅಂತ ಹೇಳೋದಾದ್ರೆ ಅದನ್ನ ಡಾಟ್ ಅಲ್ಲಿ ಮೆನ್ಷನ್ ಮಾಡ್ತೀವಿ. ಸ್ಕ್ರೀನ್ ಒಳಗಡೆಯಿಂದ ನಿಮ್ ಕಡೆಗೆ ಕರೆಂಟ್ ಬರ್ತಾ ಇದ್ರೆ ಅದನ್ನ ಡಾಟ್ ಕನ್ವೆನ್ಷನ್ ಅಲ್ಲಿ ಇಂಡಿಕೇಟ್ ಮಾಡ್ತೀವಿ. ಅದೇ ನಿಮ್ಮ ಕಡೆಯಿಂದ ಸ್ಕ್ರೀನ್ ಕಡೆಗೆ ಕರೆಂಟ್ ಫ್ಲೋ ಆದ್ರೆ ಅದನ್ನ ನಾವು ಕ್ರಾಸ್ ಆಗಿ ಇಂಡಿಕೇಟ್ ಮಾಡ್ತೀವಿ. ಸೊ ಈ ಡಾಟ್ ಅಂಡ್ ಕ್ರಾಸ್ ನೋಟೇಷನ್ ಕೆಲವು ಡಯಾಗ್ರಾಮ್ಸ್ ಅಲ್ಲಿ ಯೂಸ್ ಮಾಡ್ತೀವಿ. ಸೊ ಈಸಿಯಾಗಿ ನೀವು ಈ ಸ್ಕ್ರೂ ನ ಗ್ಯಾಪ್ ಇಟ್ಕೊಂಡ್ರೆ ಸ್ಕ್ರೂ ಮೆಥಡ್ ನ ಆರಾಮಾಗಿ ಗೊತ್ತಾಗುತ್ತೆ. ಸ್ಕ್ರೂ ಯಾವ ಡೈರೆಕ್ಷನ್ ಅಲ್ಲಿ ತಿರುಗಿಸ್ತಿರೋ ಆ ಡೈರೆಕ್ಷನ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಬಗ್ಗೆ ಡೈರೆಕ್ಷನ್ ಇಂಡಿಕೇಟ್ ಮಾಡುತ್ತೆ. ಸ್ಕ್ರೂ ಒಳಗಡೆಗೆ ಹೋಗ್ತಾ ಇದೆ ಅಥವಾ ಮೇಲ್ಗಡೆಗೆ ಬರ್ತಾ ಇದೆ ಅಂದ್ರೆ ಸ್ಕ್ರೂ ನೀವು ಟೈಟ್ ಮಾಡ್ತಾ ಇದ್ದೀರಾ ಅನ್ಟೈಟ್ ಮಾಡ್ತಾ ಇದ್ದೀರಾ ಅದ್ರ ಮೇಲ್ಗಡೆ ಕರೆಂಟ್ ಯಾವ ಡೈರೆಕ್ಷನ್ ಫ್ಲೋ ಆಗ್ತಾ ಇದೆ ಅನ್ನೋದು ಅದರಿಂದ ಗೊತ್ತಾಗುತ್ತೆ. ಸೊ ಇದು ಒಂದು ಲಾನ ನೀವು ಗ್ಯಾಪ್ ಇಟ್ಕೋಬೇಕು. ಸೊ ಯಾವಾಗ ಒಂದು ಕಂಡಕ್ಟರ್ ಮುಖಾಂತರ ನಾವು ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಪಾಸ್ ಮಾಡ್ತೀವೋ ಆವಾಗ ಆ ಕಂಡಕ್ಟರ್ ಸುತ್ತ ಒಂದು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಜನರೇಟ್ ಆಗುತ್ತೆ. ನೆಕ್ಸ್ಟ್ ಇಂಪಾರ್ಟೆಂಟ್ fundamental to remember is Faraday's law of electromagnetic induction. So as per the Faraday's law, the first law states that whenever the flux linking with the conductor changes, an EMF is induced in the conductor. Whenever the flux linking with the conductor changes, an EMF is induced in the conductor. So with respect to this, as you can see in the diagram, so we have a bar magnet and we know that the magnet, permanent magnet, so this will be producing, the surrounding of this will be having the magnetic flux, and we have a coil connected to a galvanometer or an ammeter. When we move this magnet towards the coil, the magnetic flux which are generated by or emitted by this magnet will come in contact with this coil and then an EMF will be induced. When the magnet is kept at a stationary position, even though the magnetic flux are linking with this coil, since there is no change in the flux linking, it is constant. Whatever the flux it is linking with the coil, it is constant with respect to the time. So in that case, even though you have the maximum flux linking, there won't be any EMF induced. For an EMF to induce, there must be a change in the flux that must link with the coil. Again, as in the third diagram, we are moving that back. So when we move that back, again there will be change in the flux, but now the direction of the EMF induced will be in the opposite direction. You can see in the first and the last diagram. The second law states that the magnitude of the EMF induced in a conductor is equal to the rate of change of flux linking with the conductor. So as per the first law, we quoted that whenever the changing flux links with a conductor, an EMF is induced. But with respect to the magnitude of that EMF, that depends or directly proportional to the rate of change of flux which is linking with the conductor. In the sense, how fast we move this magnet to and fro, the magnitude of the EMF induced will be more. It is directly proportional to the change of flux linking with the conductor. So we'll see that with a more clearly with an animation. So in this, you can able to see a voltmeter, a lamp, and a coil. We have a magnet. As we know that a magnet will be having the magnetic field around this. So so that we can have the visibility. So these lines you can able to see there, that is the magnetic field of lines. So as per the first law, so the magnetic field line is linking now with the coil, but this at any instant of time it is constant. At time t1 the same constant flux, at t2 the same constant flux, at t3 it is the same. So there is no change in the flux which is linking with the conductor. So for an EMF to induce, there must be a change in the flux. So when that change will come? When we move this magnet. So when I move this, you can see the bulb and the voltmeter, there is an EMF induced. And also you can see that when I move the magnet to the direction is negative, and when I move it back the direction is positive. So you can able to see the difference now. This is as per the first law. Whenever a changing flux links with a conductor, an EMF is induced in the conductor. Then the second law, as per the second law, this EMF induced, the magnitude, so how much EMF is induced, that depends on how fast you are going to move the magnet. So for example, so you can see this, so I am moving it very slowly, you can see the magnitude of the EMF induced in the lamp, right? But if I move it fast, you can see the magnitude of EMF induced. So the faster the motion you have, the more the magnitude of the EMF induced. It is directly proportional. That is what the second law says. Hope you have understood with this animation. So this is about the Faraday's law of electromagnetic induction. Next, with respect to the Faraday's law, we said that an EMF is induced. With respect to the induced EMF, we need to keep in mind the two factors. One, the conductor, and the second one, magnetic flux. Either we vary, both are essential in order to induce the EMF. So in the animation we have seen that the conductor was fixed and we were varying the magnetic field, in the sense the magnet I was moving. So due to which there was a change in the flux linking with the conductor and an EMF is induced. The EMF induced in that way we call it as statically induced EMF. The application of this is transformer. Similarly, if we keep the magnet constant and we move the conductor, then also there is a change of flux linking with the conductor, and because of this change of flux linking with the conductor, an EMF is induced, and this type of EMF induced we call it as dynamically induced EMF. For example, this principle is we use in motors and generators. We'll see with an animation which more clearly explains the concept of this induced EMF. So as you can see in this, we have magnet and we have a coil or a conductor which is connected to a lamp. So as we have quoted, so these are the two factors which are required in order for an EMF to induce. So as per the Faraday's law, there must be a change in the magnetic flux that links with the conductor in order for an EMF to induce. So now both are at stationary. I am going to move the magnet. So you can see there the EMF induced in the, and if I move it fast, the magnitude of EMF is also more. So the first case is the conductor is fixed and I am moving the magnet. So the EMF induced in this way, this one we call it as statically induced EMF. The second type what we have discussed, so now I am going to keep this magnet constant and I am going to vary this conductor. So you can see if I vary this conductor, then also an EMF is induced because there is a change of flux linking with this conductor. So as I move it fast, the magnitude will be directly proportional. So the EMF induced in this way by moving the coil and fixing the magnetic flux. So this we call it as dynamically induced EMF. Hope now you have got the clarity between statically induced EMF and dynamically induced EMF. Again, the dynamically induced EMF, which is used in motors and generators, statically induced EMF, which will be used in transformers. So now we will be mostly on to the statically induced EMF. The statically induced EMF is further classified into self-induced EMF and mutually induced EMF. So the EMF induced as per the Faraday's law, so that is given by E is equal to minus N d phi by dt, where N represents the number of turns in a coil and d phi by dt represents the rate of change of flux which is linking with this N turns. So in case of a conductor, the value of N will be 1. So in that case, the EMF induced is given by E is equal to minus d phi by dt. Where in case the minus is because the EMF induced in the coil will flow in opposite direction to the source which produce this magnetic flux. So this is as per the Lenz's law. The EMF induced will be in opposite direction of the source which is responsible for the EMF to induce. So that's why we have a negative sign. So we'll come back to the statically induced EMF, self-induced EMF and mutually induced EMF. So now we will discuss about self-induced EMF. So in case of a self-induced EMF, so as per the diagram you can see we have a coil, and for that coil we have given an alternating voltage or an alternating supply. As we have given the alternating supply, because of this an alternating current flows through the coil. And as we have seen in the initial slides, when current flows through a coil, the magnetic field will be set up around the coil. So as this is an alternating voltage supply, the current which flows through this is also an alternating current, and the flux which is generated by this is also an alternating flux. So, and this alternating flux is generated by this coil, and as we can see it is linking with the same coil. So it is generated by the same coil and it is linking with the same coil. So as per the Faraday's law, whenever there is a change in the flux which is linking with the coil, then we have an EMF induced. So this type of EMF induced is known as self-induced EMF. The reason behind this is the EMF is induced because of the flux generated by this coil by itself. And again the EMF induced, that will be in opposite direction to the source. So self-induced EMF ಅಂತ ಹೇಳಿದ್ರೆ ಏನಪ್ಪಾ ಅಂತ ಹೇಳಿದ್ರೆ, ಸೊ ನಾವು ಒಂದು ಕಾಯಿಲ್, ನೀವು ಡಯಾಗ್ರಾಮ್ ಅಲ್ಲಿ ನಿಮಗೆ ಕಾಣ್ತಿರೋ ಹಾಗೆ ಒಂದು ಕಾಯಿಲ್ ಇದೆ, ಅದಕ್ಕೊಂದು ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಪವರ್ ಸಪ್ಲೈನ ಕನೆಕ್ಟ್ ಮಾಡಿ. ಸೊ ಯಾವಾಗ ನಾನು ಆಲ್ಟರ್ನೇಟಿಂಗ್ ವೋಲ್ಟೇಜ್ ಸಪ್ಲೈ ಕನೆಕ್ಟ್ ಮಾಡ್ತೀನೋ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ಸೊ ಕರೆಂಟ್ ಯಾವಾಗ ಆಲ್ಟರ್ನೇಟ್ ಆಗಿರುತ್ತೋ ಸೊ ಅವಾಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಕೂಡ ಅದ್ರ ಡೈರೆಕ್ಷನ್ ಚೇಂಜ್ ಆಗ್ತಾನೆ ಇರುತ್ತೆ. ಬಿಕಾಸ್ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ವೋಲ್ಟೇಜ್ ಅಂತ ಹೇಳಿದ್ರೆ ನಮಗೆ ಪಾಸಿಟಿವ್ ಆಫ್ ಸೈಕಲ್ ನೆಗೆಟಿವ್ ಆಫ್ ಸೈಕಲ್ ರಿಪೀಟ್ ಆಗ್ತಾನೆ ಇರುತ್ತೆ. ಸೊ ಯಾವಾಗ ಪಾಸಿಟಿವ್ ಆಫ್ ಸೈಕಲ್ ಇರುತ್ತೋ ಕರೆಂಟ್ ಒನ್ ಡೈರೆಕ್ಷನ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ನೆಗೆಟಿವ್ ಡೈರೆಕ್ಷನ್ ಇದ್ದಾಗ ಅಪೋಸಿಟ್ ಡೈರೆಕ್ಷನ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ಸೊ ಯಾವಾಗ ಕರೆಂಟ್ ಚೇಂಜ್ ಆಗುತ್ತೋ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಕೂಡ ಅದ್ರ ಡೈರೆಕ್ಷನ್ ಚೇಂಜ್ ಆಗ್ತಾನೆ ಇರುತ್ತೆ. ಸೊ ಯಾವಾಗ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆಯೋ ಈ ಚೇಂಜ್ ಆಗ್ತಾ ಇರೋ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಏನಾಗ್ತಾ ಇದೆ ಡಯಾಗ್ರಾಮ್ ಅಲ್ಲಿ ಅದೇ ಕಾಯಿಲ್ ಜೊತೆಗೆ ಲಿಂಕ್ ಆಗ್ತಾ ಇದೆ. ಸೊ ಇದು ಸುಮ್ಮನೆ ಜನರೇಟ್ ಆಗ್ಬಿಟ್ಟು ಏರ್ ಅಲ್ಲಿ ಡಿಸಪಿಯರ್ ಆಗಲ್ಲ. ಸೊ ಇಟ್ ಈಸ್ ಕಮಿಂಗ್ ಬ್ಯಾಕ್ ಟು ದ ಸೇಮ್ ಕಾಯಿಲ್. ಸೊ ಇಟ್ ಈಸ್ ಲಿಂಕಿಂಗ್ ವಿತ್ ದ ಸೇಮ್ ಕಾಯಿಲ್. ಸೊ ಹಾಗಾಗಿ ಫ್ಯಾರಡೇ ಲಾ ಪ್ರಕಾರ ಏನ್ ಹೇಳುತ್ತೆ ಫ್ಯಾರಡೇ ಲಾ, ಯಾವಾಗ ಚೇಂಜಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಒಂದು ಸ್ಟೇಷನರಿ ಕಂಡಕ್ಟರ್ ಜೊತೆಗೆ ಲಿಂಕ್ ಆಗುತ್ತೋ ಅವಾಗ EMF ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಸೊ ಕಂಡಕ್ಟರ್ ಸ್ಟೇಷನರಿ ಆಗಿದೆ, ಫ್ಲಕ್ಸ್ ಚೇಂಜ್ ಆಗ್ತಾ ಇದೆ, ಸೊ ಅದ್ರ ಜೊತೆಗೆ ಲಿಂಕ್ ಆಗ್ತಾ ಇದೆ. ಸೊ ಹಾಗಾಗಿ EMF ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಸೊ ಈ ರೀತಿ ಇಂಡ್ಯೂಸ್ ಆದಂತ EMF ನ ನಾವು ಸೆಲ್ಫ್ ಇಂಡ್ಯೂಸ್ಡ್ EMF ಅಂತ ಕರಿತೀವಿ. ಯಾಕಪ್ಪ ಸೆಲ್ಫ್ ಇಂಡ್ಯೂಸ್ಡ್ EMF ಅಂತ ಹೇಳಿದ್ರೆ EMF ಇಂಡ್ಯೂಸ್ ಆಗೋ ಕಾರಣ ಯಾವುದು, ಇದೇ ಕಾಯಿಲ್ ಇಂದ ಜನರೇಟ್ ಆಗಿದ್ದು ಫ್ಲಕ್ಸ್. ಹಾಗಾಗಿ ಇದೇ ಕಾಯಿಲ್ ಇಂದ ಫ್ಲಕ್ಸ್ ಜನರೇಟ್ ಆಗುತ್ತೆ ಮತ್ತೆ ಅದೇ ಫ್ಲಕ್ಸ್ ಇಂದ ಇದೇ ಕಾಯಿಲ್ ಅಲ್ಲಿ EMF ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಸೊ ಈ ರೀತಿಯ ಇಂಡ್ಯೂಸ್ ಆಗುವಂತದ್ದನ್ನ ನಾವು ಸೆಲ್ಫ್ ಇಂಡ್ಯೂಸ್ಡ್ EMF ಅಂತ ಹೇಳ್ತೀವಿ. ನೆಕ್ಸ್ಟ್ ಬಂದು ಮ್ಯೂಚುವಲಿ ಇಂಡ್ಯೂಸ್ಡ್ EMF. In case of a mutually induced EMF, we have two coils, as you can see in the diagram, coil 1 and coil 2. In this case, we'll be giving the supply to coil 1, and as the alternating supply is given, alternating current flows, and because of this alternating current, alternating flux will be generated or created. And when this alternating flux comes in contact with a stationary coil like coil 2, then as the coil is stationary and the flux is changing, an EMF will be induced in the secondary coil or the coil 2. This type of EMF induced is known as mutually induced EMF. So mutually induced EMF ಅಂತ ಹೇಳೋದಾದ್ರೆ ನಮಗೆ ಎರಡು ಕಾಯಿಲ್ಗಳು ಇರುತ್ತೆ. ಸೊ ಡಯಾಗ್ರಾಮ್ ಅಲ್ಲಿ ನೋಡಿದಂಗೆ ನಿಮಗೆ ಕಾಯಿಲ್ 1 ಮತ್ತೆ ಕಾಯಿಲ್ 2. ಸೊ ಮ್ಯೂಚುವಲಿ ಇಂಡ್ಯೂಸ್ಡ್ EMF ಏನಪ್ಪಾ ಅಂತ ಹೇಳಿದ್ರೆ ನಾವು ಕಾಯಿಲ್ 1 ಗೆ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಪವರ್ ಸಪ್ಲೈ ಕೊಟ್ಟಿರ್ತೀವಿ. ಸೊ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಪವರ್ ಸಪ್ಲೈ ಇಂದಾಗಿ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೆ. ಯಾವಾಗ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೋ ಆ ಕಂಡಕ್ಟರ್ ಸುತ್ತ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಜನರೇಟ್ ಆಗುತ್ತೆ. ಸೊ ನಾವು ಕೊಡ್ತಾ ಇರೋಂಥ ಸಪ್ಲೈ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ವೋಲ್ಟೇಜ್ ಆಗಿರೋದ್ರಿಂದ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಕರೆಂಟ್ ಅಂಡ್ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಕರೆಂಟ್ ಇಂದಾಗಿ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್. ಸೊ ಯಾವಾಗ ಈ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಜೊತೆಗೆ ನಾವು ಇನ್ನೊಂದು ಕಾಯಿಲ್ ನ ಅದ್ರದ್ದು ವಿಸಿನಿಟಿ ಒಳಗೆ ತಂದು ಇಡ್ತೀವೋ ಅಥವಾ ಆ ಫೀಲ್ಡ್ ಏನು ಸ್ಪ್ರೆಡ್ ಆಗಿರುತ್ತೋ ಆ ಫೀಲ್ಡ್ ಜಾಗಕ್ಕೆ ತಂದು ಇಡ್ತೀವೋ ಅವಾಗ ನಮ್ಗೆ ಈ ಆಲ್ಟರ್ನೇಟಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಏನಾಗುತ್ತೆ ಸೆಕೆಂಡ್ ಸ್ಟೇಷನರಿ ಕಾಯಿಲ್ ಜೊತೆಗೆ ಲಿಂಕ್ ಆಗುತ್ತೆ. ಸೊ ಚೇಂಜಿಂಗ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫ್ಲಕ್ಸ್ ಲಿಂಕಿಂಗ್ ವಿತ್ ಕಂಡಕ್ಟರ್. ಸೊ ಅವಾಗ ನಮಗೆ ಕಾಯಿಲ್ 2 ಅಲ್ಲಿ EMF ಇಂಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಸೊ ಈ ರೀತಿ ಒಂದು ಕಾಯಿಲ್ ಇಂದ ಫ್ಲಕ್ಸ್ ನ ಜನರೇಟ್ ಮಾಡಿ ಇನ್ನೊಂದು ಕಾಯಿಲ್ ಜೊತೆ ಲಿಂಕ್ ಮಾಡಿ ಆ ಇನ್ನೊಂದು ಕಾಯಿಲ್ ಅಲ್ಲಿ EMF ಇಂಡ್ಯೂಸ್ ಆಗೋ ಪ್ರೊಸೆಸ್ ಇದೆಯಲ್ಲ, ಸೊ ಈ ರೀತಿ ಇಂಡ್ಯೂಸ್ ಆದ್ರೆ ಅದನ್ನ ಮ್ಯೂಚುವಲಿ ಇಂಡ್ಯೂಸ್ಡ್ EMF ಅಂತ ಕರಿತೀವಿ. ಸೊ ದಿಸ್ ಇಸ್ ಅಬೌಟ್ the types of EMF induced. And next, so we have a little history to discuss. So this during the period of the 80s, so which was the preferred choice, either the DC current or the AC power. So there was a war between Nikola Tesla and Thomas Alva Edison. So Tesla was in the favor of alternating current and Edison in the favor of DC current. So even though today we use more the DC power supplies, so for mobile charging we require a DC, for desktop PCs, for laptops, for modern LED televisions, even for LED lamps we are using DC power supply. So we'll be taking the AC from the AC outlet, we'll convert that into DC and then we are utilizing. So in that case, why can't we have a DC transmission system? So why we have only an AC transmission system? So this I'm speaking, keeping in mind that we are in the era of 1880s. So during that time, so the war of currents will be won by Nikola Tesla because of the one electrical device which is known as the transformer. Because during that period, converting a DC voltage into a different higher level or a lower level, it was a very complex task. And there was no much development in the semiconductors which will be utilized as of now, like the IGBTs or power MOSFETs. And because of this one guy, the transformer, so Nikola Tesla was a winning person, and even today we are using that, and it is because of the transformer. So AC transmission system ಇವತ್ತಿಗೂ ಕೂಡ ನಾವು ಏನು ಯೂಸ್ ಮಾಡ್ತಾ ಇದೀವೋ, ಸೊ ಅದಕ್ಕೆ ಮುಖ್ಯವಾದ ಕಾರಣ ಬಂದು ಮುಖ್ಯವಾದ ಕಾರಣಗಳಲ್ಲಿ ಇದು ಒಂದು ಕೂಡ, ಯಾವುದು ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್. ಈ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಇಂದಾಗೆ ನಾವು ವೋಲ್ಟೇಜ್ ನ ಸುಲಭವಾಗಿ ಎಲ್ಲಿ ಬೇಕೋ ಅಲ್ಲಿ ಜಾಸ್ತಿ ಮಾಡಬಹುದು. ಅಂದ್ರೆ ಜನರೇಟಿಂಗ್ ಸ್ಟೇಷನ್ ಹತ್ರ ಜಾಸ್ತಿ ಮಾಡ್ತೀವಿ, ಡಿಸ್ಟ್ರಿಬ್ಯೂಷನ್ ಪಾಯಿಂಟ್ಸ್ ಹತ್ರ ಕಮ್ಮಿ ಮಾಡ್ತೀವಿ. ನಾವು ಸ್ಟೆಪ್ ಡೌನ್ ಮತ್ತೆ ಸ್ಟೆಪ್ ಅಪ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ಸ್ ಅಂತ ಕೇಳಿರ್ತೀವಿ. ಯಾವುದೇ ರೀತಿಯಾದಂತ ಬೇರೆ ಏನೇ ವಸ್ತು ಬೇಕಾಗಿಲ್ಲ, ನನಗೆ ಒಂದು ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಇದ್ರೆ ಸಾಕು. ಅದು ಸ್ಟೆಪ್ ಅಪ್ ಬೇಕು ಅಂದ್ರೆ ಸ್ಟೆಪ್ ಅಪ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಯೂಸ್ ಮಾಡ್ತೀನಿ, ವೋಲ್ಟೇಜ್ ಕಮ್ಮಿ ಮಾಡಬೇಕು ಅಂತ ಅಂದ್ರೆ ಸ್ಟೆಪ್ ಡೌನ್ ಟ್ರಾನ್ಸ್ಫಾರ್ಮರ್ ಯೂಸ್ ಮಾಡ್ತೀನಿ. ಬಟ್ ಡಿಸಿ ಕರೆಂಟ್ ಅಲ್ಲಿ ಅಥವಾ ಡಿಸಿ ವೋಲ್ಟೇಜ್ ಅಲ್ಲಿ ಆ ರೀತಿ ಮಾಡಕ್ಕೆ ತುಂಬಾ ಕಷ್ಟ ಆಗ್ತದೆ. ಸೊ ಹಾಗಾಗಿ ಆ ವಾರ್ ಆಫ್ ಕರೆಂಟ್ಸ್ ಅಲ್ಲಿ ಟೆಸ್ಲಾ ಅವರು ವಿನ್ ಆಗ್ತಾರೆ. ಬಟ್ ಈಗ ಇವನ್ ನಮ್ಮ ಇಂಡಿಯಾದಲ್ಲಿ ಕೂಡ ನಾವು ಹೈ ವೋಲ್ಟೇಜ್ ಡಿಸಿ ಟ್ರಾನ್ಸ್ಮಿಷನ್ ಸಿಸ್ಟಮ್ಸ್ ನ ಎಸ್ಟಾಬ್ಲಿಷ್ ಮಾಡಿದೀವಿ. ಸೊ ನಮ್ಮ ಇಂಡಿಯಾದಲ್ಲಿ ವರ್ಲ್ಡ್ಸ್ 5th ಲಾರ್ಜೆಸ್ಟ್ ಡಿಸಿ ಟ್ರಾನ್ಸ್ಮಿಷನ್ ಸಿಸ್ಟಮ್ ಇದೆ. ಸೊ ಅಂಡ್ ಇದು ಒಂದು ಒರಿಸ್ಸಾ ಇಂದ ನಮ್ಮ ಕೋಲಾರ ಕರ್ನಾಟಕಗೆ ಕನೆಕ್ಷನ್ ಇದೆ. ಅಂಡ್ ಇದನ್ನ NPTCL ಅವರು ಮೇಂಟೈನ್ ಮಾಡ್ತಾ ಇದ್ರು. ಸೊ ಇನ್ನೊಂದು ಅಲ್ಟ್ರಾ ಹೈ ವೋಲ್ಟೇಜ್ ಡಿಸಿ ಟ್ರಾನ್ಸ್ಮಿಷನ್ ಸಿಸ್ಟಮ್ ಅಂತ ಸೆಟಪ್ ಮಾಡ್ತಾ ಇದ್ದಾರೆ ಫ್ರಮ್ ಡೆಲ್ಲಿ ಟು ತಮಿಳ್ನಾಡು. ಸೊ ಅಪ್ರಾಕ್ಸಿಮೇಟ್ ಆಫ್ ಅರೌಂಡ್ 1830 ಕಿಲೋಮೀಟರ್, which is with the help of ABB, a Swedish company, and in tie-up with BHE, our Indian-based company. So this is little history to know about the currents. And at next, this is just for your reference. As you have seen, many of the conversions we have used in the single-phase AC circuits derivations. So we have in most of the cases we have changed the sine omega t into cos omega t minus 90, or cos omega t to sine omega t plus 90. So even in this, during the derivations of the EMF equation of transformer, we will be using minus cos omega t. So that minus cos omega t can be written as sine omega t minus pi by 2 or minus 90. So that is minus cos alpha is equal to sine of alpha plus 270, which is also equal to sine of alpha minus 90 degree. So how this can be easily written with the help of this diagram. So a graphical representation to easily identify that. So you can see that we have plus sine alpha, minus sine alpha, plus cos alpha, and minus cos alpha. So if I want to represent this, I'm taking the example of this minus cos alpha in terms of sine. So if I take this minus cos alpha, I can write this in terms of sine as plus sine alpha, okay, sine alpha plus 270 degree, okay, 90, 180, 270. So okay, in the counterclockwise direction. That is what here written, sine alpha plus 270 degree. So from this point, like this. Or if I write in clockwise direction, it is sine alpha minus 90 degree or pi by 2. So this is the same minus cos alpha can be written as sine alpha minus 90, sine alpha, which is a plus minus 90. So that is pi by 2. So this Just for your reference, we'll be using in module 1, 2 as well as in this chapter. Hope you have understood the basics. We'll be starting in the next part with the actual topics of your module. Thank you.